So the question is about 4.79. Which asks us to rank some ions in order of increasing number of unpaired electrons. So that would be starting with the one with the fewest unpaired electrons to the most unpaired electrons. So the way to do that is to look at the atom in its neutral state to see where the electrons would be, and then adjust the electrons to see, once you adjust them, with the number that you have remaining, are they going to be coupled together in orbitals, pairing up, or are there going to be a bunch of unpaired electrons? So to draw an orbital diagram would be the best way to do that. So the ones here that we're meant to look at are titanium 3+, Fe2+, V3+, Cu+, and Mn4+. So if I look at where these ones are on the periodic table, they're all here in the G block. And so that means if I'm thinking about their normal electron configuration, if they were neutral, I would have the first three energy levels, including the 3s and the 3p filled. Then I'd have 2 electrons in the 4s and then some number in the 4d, depending on which element I'm talking about. So each one of these has a core that is argon plus a 4s2. And then the titanium would have a 3d2 beyond that. The iron would have a 3d6. The vanadium would have a 3d3. The copper would normally have a 3d9, but if you recall, that was one of the very few exceptions we talked about. So that would actually have a 4s1 3d10 for its ground state, and then the manganese is a 3d5. And so again, just to point out, we talked about the method for solving a problem like this is if you have an ion, the best way to do it is to first start with what the electron configuration would be for the neutral atom, and then if it's positive, take electrons away from the outermost energy level first, take enough electrons away from it until the remaining electrons produce this imbalance in charge that's given to you. So those are what the neutral electron configurations would look like. So what I need to do is to come up with the ones for the charged ions. So for titanium, if I had an argon 4s2 plus a 3d2, if it were neutral, but I were going to give it a 3+ charge, I would have to take 3 electrons away. And the general idea here for most examples, with a few exceptions, you want to take away the valence electrons first, right? The 4th energy level is a higher energy level than the 3rd energy level. So when I'm removing electrons, I always remove them from the subshells with the highest value for N, the highest principal energy number, the highest energy level. So for titanium, if I'm going to remove 3, I've got to remove the 2 from the 4s first, and then 1 from the 3d. So the titanium's electron configuration will be argon 3d1. So since all the electrons have to pair up in orbitals to get to argon, right, the argon has to complete 3s. That means they're all filling up the orbitals, pairing up with opposite spins. So if I have that, then plus only 1 more electron in the 3d, that's 1 unpaired electron. For the iron, I would do the same thing. So for the iron, I'm giving it a +2 charge. So normally I would take away the 2 electrons in the 4s, and it would be 3d6. Anyone see a problem with that? Right, so that's kind of similar to a situation where I would have, I'd be close to a half-filled d subshell. So if I could take one of the electrons out of here, if I had another place to put it where it would be similar in energy, that would be better because it would make the 3d exactly half full. So that's really what I need to do here. So for the iron, when I start with 2 electrons in the 4s and 6 in the 3d, I'm not going to follow the normal rule here and remove them all from the 4th energy level first, because if I do, then I won't have that nice half-filled 3d subshell. So I want to remove 1 from the 4s and 1 from the 3d, and since they're close in energy, I can do that. And that will make both the 4s and the 3d exactly half-filled. So that actually has 6 unpaired electrons, because if we look at the 4s and the 3d, and I am going to put 1 in the 4s and 5 in the 3d, remember that when you have equal energy orbitals, and I have electrons to put in there, they should spread out first before they start to pair up. So that creates a total of 6 unpaired electrons. So then if I look at the other ones, vanadium plus 3, again, I want to remove the 4th energy level electrons before I remove the 3rd energy level electrons. In this case, I'm removing 3. So I would take 2 out of the 4s and 1 out of the 3d. So that one is going to give me argon 3d2. And so that would just be a situation where I have nothing in the 4s and 2 electrons in the 3d, but they're not going to pair up because I have enough orbitals to spread them out with the same spin, so that's going to give me 2 unpaired electrons. With the copper plus, we said that one has one of our exceptions to the idea of filling up the 4s before I start to fill up the 3d, and there's only 1 electron in the 4s, so if I have a plus 1, that would be the electron I would remove. I don't want to break up the completely filled 3d. The whole point of making it completely filled is because that makes it more stable than having the electrons in the 4s. So if I'm going to remove one, I'm going to remove it from the 4s, and so that's going to give me the argon core plus a 3d10. So if I have 10 electrons in the 3d, that means it's completely filled. All the electrons are paired, so I have 0 unpaired electrons. And then for the manganese, I'm going to remove 4. So I would take them first out of the 4s. That's 2. And so I then remove 2 more from the 3d. And I would end up with an argon 3d3. So that gives me 3 unpaired electrons. So then I can rank them from fewest to most. So it will be the copper plus with 0 unpaired electrons. Then the vanadium 3 plus with 2 unpaired electrons. Then the manganese 4 plus with 3 unpaired electrons. Oh, I left out the titanium, sorry. The titanium 3 plus only has 1. And then the iron 2 plus has 6, so it would be by far the most unpaired.